Hello everybody, it's me, Jacob, aka the Number Ninja, aka Sensei. Welcome back to the dojo. Today we're going to be covering laws of exponents. So it's going to be a little bit more definition based today. I will provide you a couple examples, but it's mostly just so you have an idea of what to expect when working with exponents rather than hopping into specific complicated problems. Before we begin on the laws, there's going to be around 8 of them that we covered today. I did just really quickly want to talk about what the structure of an exponent. There's really only 2 things that we need to worry about. We will have a base, in this case I'm going to do 4, and then we will have the exponent itself, which here I'll just say is a 3. And those are literally the only 2 components that we care about so far. 4 would be called the base, 3 would be called the exponent. They're both going to be important as we go forward here. So with that in mind, let's move on to our first rule here, product of powers. So product, again, this means multiplying, right? So it's multiplying 2 powers together. Here is kind of the abstract rule, and then I'll also give you real examples, that way you can have a better understanding of what we're talking about. So product of powers is if we have a base a to the power of n, and we are multiplying that with another value, also base a to the power of n. And what this rule says is that if we do this, we will get the same base of a, but our exponent will now just be adding the 2 previous exponents we had together. And of course it's an equation, so you can also go this way around and break a combined value down into 2 separate exponents. So here's an actual view of what that would look like, just so you're less confused by the random numbers, right? Let's say we had 3 to the 2nd power, right, a base of 3, and we're multiplying this by 3 to the 7th power. Obviously, we can do the math and get 3 to the 2nd power and 3 to the 7th and just multiply those together, but that's not easy to do, particularly with something like 3 to the 7th. So instead what we're going to do is we're going to follow this rule, right? So we should have the same base, which means our base would still be 3, but our new exponent will be m plus n, which in this case is 2 plus 7, meaning our value is actually 3 to the 9th power. So that's product of powers. It's, as long as you remember what you're supposed to do here, you're fine. But just remember, if we have the same base, we add together the exponents. It is important to note, this does not work if the bases are different. So if this was a 2 to the 2nd power instead, we could not do this. It doesn't work. The values have to have the same base. Okay, hopefully that wasn't too bad. Next up, we are going to go into the next one here, which is quotient of powers. Quotient means division. So it's basically the same thing, but we are dividing this time. So it's the idea of if we ever have a to the m divided by a to the n, division is kind of like the opposite of multiplying, right? So instead of adding these exponents together like in the previous one, we subtract. So we actually get m minus n as our new our new exponent with the same base again. And the same thing applies as with the power or the product of powers. We need the same base for this to work. And also same thing, you can go the other way around as well. So here is a number example for this one. Again, it's very similar. Just think division makes the number smaller, so we're going to subtract, whereas the product makes the number larger, so we're adding in the previous one, right? But the same thing applies. 7 to the 3rd power, for example, if we're dividing that by 7 to the 2nd power, we would expect again to have the same base of this 7 here, but our exponent will now be m minus n, which gets us 3 minus 2, which is 1. You can also see this rewritten in a different form as 7 to the 3rd power divided by with the division sign like this, just because, you know, fraction bars work as division signs and a fraction, right? You get the same answer either way. That's just something to keep in mind. And I guess an example of how you can do this backwards, I know I didn't really cover in the previous one, but the same thing applies. Let's say we had 4 to the 5th power. We can rewrite this actually as 4 to the 2nd power times 4 to the 3rd power using the product of powers rule. But we can also write it, if we go this way, as something like 4 to the 9th power divided by 4 to the 4th power. So just goes to show that you can rewrite the same exponent multiple different ways using these two rules here. And again, these only work if the base is exactly the same. We cannot do it with different bases. So those two are similar. They're kind of like twins, and not really twins, but I guess brothers, you could call them, siblings. They do the same thing, but with different operations, right? Power of powers is a little bit different. It's, again, the name kind of gives it away a little bit, but power of powers means we're taking an exponent and raising it to another power. So this would look something like, again with our a to the m power. Oh, sorry, my pen broke. Okay. Oh, it's still gone. I don't know why it's doing that. 1 second. Now it's not going away. There we go. All right, but it would be like a to the m power, but all of this then raised to the n power as well. So as you can see, a power of a power here is what we got going on. This one's a little bit different. When we do this, we would expect to keep our base as a, but our exponent becomes m times n. Okay, so previously we were doing adding and subtracting, which is what happens when we have division or multiplying of the bases. But here we technically have an exponent of the power itself, not the base, and that's why we're going to be doing some multiplying here. So a real example of this would be something like 2 to the 3rd power raised to the 4th power. This would end up being, again, we're going to keep the 2, but what is 3 to the 4th power? That is 12. And the reason why this one's a little bit different is because you can actually rewrite this. Remember, an exponent just tells you how many times to write the number multiplying to itself, right? So this really means we're multiplying 2 to the 3rd power 4 times. And if we think about that, and we write it out like this, this is actually a product of powers like we did earlier. So we can use that same rule in this case, the product of powers rule, because these are all the same base, and add all of our variable exponents together. Because really we're multiplying all of them together. And if we think about that, 3 plus 3 plus 3 plus 3 is 12. Right? So power of powers is a rule that's actually coming from the product of powers we just talked about, where we're just saving ourselves some time and acknowledging that because there's going to be 4 of these 3's and we're actually adding them all together, we can just do 3 times 4. So hopefully you remember that one because it will save you a lot of time. All right, so let's now move on to the next one, which is going to be the power of a product. This one, different again. So what we're expecting here is actually, if you notice, it's not a product of a power, it's a power of a product. So this means if we're multiplying values together already, let's say a times b, okay, 2 random values. If we're multiplying these together and then raising that to a power, which we will call m, what we can expect is we can actually break this down. So instead of having to do the multiplying first, sometimes we can't. We can break it down to a to the m power times b to the m power. So this one's a little bit different because normally we're keeping the base the same and changing the exponent, but this is a rule where we can actually change the where we can change the bases but keep the exponent the same. So as another example, this obviously also goes backwards as well, just like the previous one. All of these work one way or the other because it's an equation. But a real life example, or a real number example, let's say we're doing 3 times 7 to the 3rd power. If we wanted to do this normally, we would have to get 21 to the 3rd power, because that's what 3 times 7 is. That's obviously not easy to do. With a calculator, sure, but if you have to do it by hand, that would be very difficult. So we can actually break it down and rewrite it as 3 to the 3rd power times 7 to the 3rd power. And now it's a little bit more manageable, right? We know 3 to the 3rd power. We can figure that out by multiplying together 3, and same thing with the 7, right? We talked about cubes on the last video and cube roots. So these are actually doable by hand. They're still not easy, but they're doable by hand, whereas 21 to the 3rd power is kind of a lot more difficult. You'll get the same answer either way, which is why this is a rule in the first place. But sometimes there are reasons to break it apart, like we have a variable that we don't know the value of, and we're trying to solve for it, that kind of thing. So an example of going the other way around is actually we could take this, let me do a new one. Let's say we had 4 to the second power times 8 to the second power. We could actually rewrite this as 32 to the second power, multiplying the bases together and keeping our exponents the same. So another important thing to note for this one, previously we had the situation where we needed the bases to be the same, but the exponents could be different. This one is the opposite, right? We need the exponent to be the same, right? They both have to be m, but the bases can be different. So something to keep in mind as we're going forward here. Power of a quotient is the sister rule to what we just talked about with products, but now with division. So this one is very similar, but the idea is if we're dividing a variable or a value by another value, and that whole thing is being raised to a exponent, just like the last time, we can actually rewrite it as the first one to the exponent divided by the second value to the exponent. And again, this can also be written as a fraction bar just because that's the same thing as division. So again, it's the sibling of the previous one of the power of a product. We're just doing it with division now instead. So nothing too crazy to talk about here. Again, just to be safe, I will show you an example of what you can kind of see that being useful. Or not even useful, but just an example of what it would look like. Let's say we have 3 divided by 7. I keep choosing 3 and 7, but don't worry about that. Again, let's go with the third power now. We can actually do this as a fraction, but that's not the point. We can rewrite it as well as 3 to the third power divided by 7 to the third power. And again, the examples I'm using here aren't making it the most useful, but when we get into more advanced stuff, you'll see why this is helpful for sure. All right, now switching gears a little bit into negative exponents, which are different than what we've been talking about. This is less a rule of how to, okay, a little sneak peek here, but this is more how to deal with negative exponents, which we will see from time to time. And it's a little bit counterintuitive, but sorry, that was a bad A. Let me fix that. But what we can expect with a negative exponent would be something like this, a to the power of negative m. The cool thing about negative exponents is that it doesn't really matter what either of these are. It just means we take the reciprocal of what we have, which means flipping it over to the other side of the fraction. So in this case, our a to the negative m is actually the same thing as 1 divided by a to the m. So the important thing to note here is our value or our exponent changes back to a positive value when we flip it over, but the exponent still remains as an m and the base does not change, it still stays as an a as well. And this works the other way around as well. Let's say we had something in our denominator, so instead of that, let's say it was 1 over b to the negative m. Because this is in the denominator, flipping it over and taking the reciprocal actually brings it into the numerator. So we would end up with b to the m. And again, it stays as an m but becomes positive because we have flipped it over now. So a few examples of this, because this one is a little bit tricky to get your head wrapped around. If we had 7 to the negative 2 power, the negative does not mean we're making our base negative. That's a common mistake people make, right? We wouldn't end up with negative 49 here. That would be incorrect. Oops. We would flip it over into our denominator, making it 1 over 7 squared, and then we would actually get 1 over 49. So that is kind of how that works. Sometimes, let me do one where it starts at the bottom as well. 3 to the negative 2, again with the 7s and 3s, but this would not be 1 over a negative 9. We would flip it over and actually get 3 squared, technically over 1, because that denominator doesn't disappear. But when it does become a 1, we're saying that we're dividing by 1, and that doesn't actually matter. So whenever we have a 1 in the denominator, we just don't write it out, because it's just easier this way. And then 3 squared is 9. Sometimes you will have a situation where it's already, like let's say it's a fraction. You will already have a value in your denominator. So let's say we actually have 4 to the negative 3 power over 6. The -3 in this case is actually only on the 4, so the 4 is the only thing affected by it, which means our 6 actually stays where it is, but we're moving this 4 down to the denominator, which means our numerator is now empty. But we also just multiply that to whatever is already there. So in this case, that would then become 6 times 4 to the 3rd power. And we can, do the math and figure that out, but that's not really the point. So hopefully that explains negative exponents. And now just 2 last ones to cover here. These ones are very straightforward, so I'm not going to talk about them very long. An identity exponent is just something to the 1st power, and it's called the identity exponent because that value will not change. Anything to the 1st power just means you're basically multiplying it to nothing, right? Because you're only multiplying it once. You're just doing a times nothing, but not times 0, just nothing there. So it stays a. An example of this, let's say this is a 9 to the 1st power. Well, if we have 1 9, that means we have 9. Hopefully that one's straightforward. Just that's what they mean when they say identity exponent. 0 exponent is also straightforward. It's just a rule that says no matter what we have, any number, if it's to the 0 power, it becomes a 1. That's a little bit confusing because you would expect it to be a 0, but we're not saying, again, that we have nothing, right? We're saying that we're kind of multiplying 0 of these values. And if we're multiplying 0 of these values, it just ends up being 1 for mathematical reasons. I wouldn't worry too much about the actual theory of that. Just know that no matter what number we have here, if it's to the 0 power, it is 1. It doesn't matter if it's like a -40 to the 0. It doesn't matter if it's a billion to the 0. It just always becomes a 1. So yeah, that is actually all of the laws of exponents that we had to cover today. Hopefully they were easier to understand now that we went over them. This really, again, we're laying the groundwork for actually using these in solving problems. So for now, it's just more focused on remembering what they do and how to use them. Hopefully their names make it a little bit easier to remember because most of the names explain what's going on. And yeah, thanks again for training with me today, guys. I'll see you next time. Thanks.